Hello! In this video, we are going to prove the following theorem. Let x be a real number and consider the following sequence. Then the sequence converges to 0. Now, to prove this, we can first observe the following. The absolute value of xn plus 1 is less than or equal to absolute value of xn over 2 for all n. So this is just scratch work, but if we apply this fact repeatedly, well, let's first note absolute value of x0 over 2 is equal to absolute value of x over 2. But by this fact, we know that absolute value of x0 over 2 is greater than or equal to absolute value of x1. But then if we divide everything by 2, we know that absolute value of x1 over 2 is greater than or equal to absolute value of x2. Then if we divide everything by 2 again, we get this, but this guy is greater than or equal to absolute value of x3. If we divide everything by 2 again, we get this, but then, again, absolute value of x3 over 2 is going to be greater than or equal to absolute value of x4, and you can keep doing this. We see that absolute value of x4 is less than or equal to absolute value of x over 2 to the 4, but in general, we should expect the following. The absolute value of xn is less than or equal to absolute value of x over 2 to the n for all n. And so, the first thing we are going to prove is that this is true. And we're going to show this by induction. And so, let's start with the base case. In the base case, we're trying to show that absolute value of x0 is less than or equal to absolute value of x over 2 to the 0. Well, we know that x0 is equal to x, so absolute value of x0 is equal to absolute value of x, which is, of course, equal to absolute value of x over 2 to the 0. So we have absolute value of x0 is less than or equal to absolute value of x over 2 to the 0. So we have shown that this is true in the case where n is equal to 0. So this completes the base case. Now let's move on to the induction step. In the induction step, we are assuming that absolute value of xn is less than or equal to absolute value of x over 2 to the n for some n. The whole goal of the induction step now is to show that this is also true for n plus 1. So really, we want to show absolute value of xn plus 1 is less than or equal to absolute value of x over 2 to the n plus 1. Well, let's first write out absolute value of xn plus 1. Well, by definition, xn plus 1 is this expression. And we know that the absolute value of the fraction is just the absolute value of the numerator over the absolute value of the denominator. And we actually don't need the absolute values in the denominator because the expression in the denominator is positive. But now, we notice 1 plus xn squared is greater than or equal to 1. And therefore, the square root of this guy must also be greater than or equal to 1. If we add 1 on both sides of this inequality, we get this. But then if we take the reciprocal of both sides of this inequality, the sign of the inequality will be flipped. So we get this. But then if we multiply both sides of this inequality by absolute value of xn, we get this. So this guy is less than or equal to absolute value of xn over 2. And then from here, we remember by our induction hypothesis that absolute value of xn is less than or equal to absolute value of x over 2 to the n. So if we take this inequality and divide 2 on both sides, we get that this guy is less than or equal to absolute value of x over 2 to the n plus 1. And so we have shown that absolute value of xn plus 1 is less than or equal to absolute value of x over 2 to the n plus 1. So this completes the induction step. And so, this closes the induction, and so our claim is proven. And so, this should be able to help us prove that this sequence converges to 0. Now, to prove that this sequence converges to 0, let's recall what it means by definition for a sequence to converge to 0. This means the following. It means for every epsilon greater than 0, there exists a positive integer capital N, such that for all n greater than or equal to capital N, the absolute value of xn minus 0 is less than epsilon. So, to prove the sequence converges to 0, all we have to do is prove this statement. And so, to prove this statement, since we're trying to prove a statement about every epsilon greater than 0, let's give ourselves an arbitrary epsilon greater than 0. And from here, we want to find a positive integer capital N such that this is true. Now, to see how we should choose capital N, well, whatever capital N is, we want to end up showing that for all n greater than or equal to capital N, the absolute value of xn minus 0 is less than epsilon. So, what we're going to end up going through is, we're going to have absolute value of xn minus 0. This is equal to absolute value of xn, and by the result we just proved, this is less than or equal to absolute value of x over 2 to the n, but we want to somehow make this guy less than epsilon. Now, to say that absolute value of x over 2 to the n is less than epsilon is equivalent to if we swap 2 to the n and epsilon. Right? So this inequality is equivalent to this. But what we can do here is, we notice 2 to the n is bigger than n. And n is just an arbitrary integer greater than or equal to capital N. So all we have to do is choose a positive integer capital N that is bigger than absolute value of x over epsilon. Because if we do that, well then it follows for all n greater than or equal to capital N, we have 2 to the n is bigger than absolute value of x over epsilon, and that's equivalent to saying absolute value of x over 2 to the n is less than epsilon, but then we have absolute value of xn minus 0 is less than epsilon. And so it follows, for all n greater than or equal to capital N, absolute value of xn minus 0 is less than epsilon. So, yeah, all we have to do is choose a positive integer capital N bigger than absolute value of x over epsilon. The claim is, with this choice of capital N, it follows that for all n greater than or equal to capital N, absolute value of xn minus 0 is less than epsilon. And so to prove that statement, since we're trying to prove a statement about every integer greater than or equal to capital N, let's give ourselves an arbitrary integer greater than or equal to capital N. Call n. And from here, we want to show absolute value of xn minus 0 is less than epsilon. Well, what we notice in our scratch work is the following. We had 2 to the n is bigger than n, and n is greater than or equal to capital N, and capital N is bigger than absolute value of x over epsilon. So, 2 to the n is bigger than absolute value of x over epsilon, but to say that is equivalent to if we swap 2 to the n and epsilon. Right? But then from here, we're able to show absolute value of xn minus 0 is less than epsilon. Because we had absolute value of xn minus 0 is equal to absolute value of xn, which is less than or equal to absolute value of x over 2 to the n, and we know that this guy is less than epsilon. So we see absolute value of xn minus 0 is less than epsilon, which is exactly what we wanted. And so we have proven this statement, which means we have proven that our sequence converges to 0. And so this completes the proof. And so yeah, that's pretty much it for this video.